All right, open up your book to section 7-4. We're on page 357 in your book. And the title of this section is Arcsine, Arctangent, Arccosine, and Trig Equations. And the objective is to find algebraically or numerically the solutions to equations involving your circular or your trig functions, that is your sine, cosine, or tangent of one argument. All right, and we've already covered now the arc-cosine inverse relationship. We did that actually back in the previous chapter. We've now covered in this section the arcsine inverse relationship as well as the arctangent inverse relationship. So we've now seen how to solve these equations algebraically. All right, so let's take a look at a couple of variations of solving these equations. In example 3 here, it says to solve the equation cosine squared plus sine of theta plus 1 is equal to 0. Let's write that down. Cosine squared of theta plus the sine of theta plus 1 is equal to 0. And they give us a domain here. They're saying theta is on the interval from negative 90 degrees to a positive 270, but not including the 270. If you wanted to write that as an inequality, that would mean you got negative 90 is less than or equal to theta, which is less than 270 degrees. All right, remember we're not including the 270 there. All right, so that's the domain they want me to work on. All right, so to solve this equation, the first thing you should recognize is there's a quadratic term in here. It's cosine squared. And I guess the other thing that you should notice, I can circle that. The first thing you should notice is that thing's quadratic. The other thing you should notice is that you've actually got two different trig functions here. I got cosine and I've got sine. And that's going to cause a bit of a problem here. The quadratic is not so much of a problem, but the fact that I've got two different trig functions, that's going to cause a problem. So what you need to do on a problem like this, and not all of them be set up this way, but on a problem like this, you need to get this in terms of one variable. So the way to do this is to think about your Pythagorean properties and take this cosine squared that you've got here and rewrite it in terms of sine. I know that cosine squared plus sine squared is equal to 1, or in other words, cosine squared is equal to 1 minus sine squared. Remembering those properties is going to be very important. So hopefully you've committed those to memory, but if not, again, take some time to do so. So cosine squared, I'm going to replace that with 1 minus sine squared of theta. The rest of this will stay the same. And now let's rewrite this so that my sine squared term is first. So I'll have a negative sine squared of theta. I've got a plus sine of theta. I've got a 1 out in front here, and I've got a 1 here at the end, so that's a plus 2. That's equal to 0. Now what I've got is a quadratic equation. This here is a quadratic equation. And I would suggest to you that the same way you would solve a quadratic equation, let's replace sine of theta with a. If I had the opposite of a squared instead of the opposite of sine of theta squared, plus a plus 2 equals 0, this is clearly a quadratic equation. Oops. And I could use my quadratic formula to solve something like that. I could even factor it if it factors nicely, but definitely a quadratic equation. We've now seen how to solve these many times. The same way that I would solve this quadratic equation for a, I could do the same thing to solve what I started with for sine of theta. Not theta, but sine of theta. In fact, if it helps you to stick with this in terms of a, then I would suggest that you factor out probably a negative here would be the first step to do. So write that as a negative times a squared minus a minus 2 equals 0. That might be an easier way to factor this. You can factor with a negative in there still, but it might be easier this way. So this factors nicely here. If I subtract 2 and add 1, a minus 2, a plus 1. There are my two factors, which now I can find my solutions. A would be equal to 2, and A would be equal to a negative 1 would be my solutions. That's how we'd solve that if it was in terms of A. I'd suggest to you that we can do the exact same thing with it in terms of sine of theta. So let's go back to our original and go through these same steps here. Let's start out by factoring out the negative. So write this as sine squared theta minus the sine of theta minus 2 is equal to 0. And now factor that. So to factor that, I've got two linear factors here I'm trying to come up with. I have to have the sine of theta times the sine of theta in order to get sine of theta squared. And again, I need a product of a negative 2, but a sum of a negative 1. So that must be a minus 2 and a plus 1 to do that. Now, if it doesn't factor nicely, just like up above here, we could have ran that through the quadratic formula and used that to solve this. You could do the same technique on this one here. That is, I could have taken this and I could have run it through my quadratic formula and said that A is equal to the opposite of 1 plus or minus the square root of the 1 squared minus 4 times the negative 1 times 2. That's all divided by 2 times the negative 1. We could have run that through a quadratic formula and come up with the same two solutions. You could do the same thing down here with this, but realize that instead of finding out what A equals like I did up above, I'm going to find out what the sine of theta is equal to. I would add the sine of theta is equal to, I've already factored out the negative 1. I'm not going to write it that way here as I write this out here, but it'd actually be a negative 1 plus or minus the square root of B squared would be a 1 squared minus 4 times A, which is a negative 1 times C, which would be a positive 2. That's all over 2A. Oops, 2 times a negative 1. Okay, that's the exact same thing we have up above, but instead of A, I've got sine of theta. Exact same thing. So you can do it that way as well. If you get stuck with the factoring, don't let that stop you. Just use your quadratic formula. But now with this, I can rewrite this as two separate equations. Remember, the way that we solve this is we take that first factor and we set it equal to 0. So I have the sine of theta minus 2 equals 0. That's one equation. And the other equation that I have here is that the sine of theta plus 1 is equal to 0. I've got these two equations to solve. Let's start with the one that's on the left because that's the easy one. You might recognize right here at this point what the solution is going to be, but definitely I think once you say sine of theta is equal to 2, that should be a big hint to you what's going to happen here. Think of the range of your sine function. The range of sine is only from negative 1 to 1. Sine function oscillates between a low of a negative 1 and a high of 1. It never is equal to 2. There's no solution here. So that's why I say that's the easy side, because there's no work to do. Over here on the right, we got some work to do, though. So move the 1 to the other side. We've got sine of theta is equal to a negative 1. And now at this point, again, we're going to use arc sine to solve this. Don't use sine inverses. You're only going to get one solution, and there might be more than one solution here. So make sure you get all the solutions by using arc sine. Theta is equal to the arc sine of a negative 1. And again, once you get the variable isolated over on the left, which we already have, it's just theta. Then you can replace arc sine with what it's equal to. That's that piecewise function, remember. So this is equal to the sine inverse of a negative 1 plus, now this is in terms of theta, and you can even look at the domain they've given you. That's another hint, obviously, what mode you're in here. This is in degrees. Don't put this in terms of pi here, in other words. So it's plus 360 times n. And then the other half of this, again, because we are in degrees, it's not pi minus, it's going to be 180 degrees minus sine inverse of a negative 1 plus the 360n. And now all we have to do is figure out what value of n do we have to pick for each of these to get the right solution. So go back to not the very original problem here, but this new problem that we've started out here. In fact, I would even suggest that you jump to this right here. You could use this one or the line above it. Either one would work. But if I think of graphing the sine of theta equal to negative 1, we're looking for the solutions from that. on the domain from negative 90 to positive 270 they gave us. So let's sketch that. Sine of theta I know is something that looks like this. Well, I guess I can sketch that too. So here's sine of theta. This would be at a negative 180, but I only want to go from negative 90, so I'm going to start with that. And I only want to go to 270, so 270 is the location of that lower bound there that I've got. So there's the domain that we're working on. We're including negative 90 degrees, but not the 270. And we're trying to set this equal to a negative 1. So negative 1 is down here. So where we hit those lower bounds, this is negative 1. So we're looking for this solution right here because they said to include, this is a square bracket, include the 90 degrees. But it was a parenthesis there for the 270, so we're not including that. So I don't want this solution over here. Now, because we're setting the sinusoid equal to its highest point or its lowest point in this case, in either one of those cases, I'm going to find out that the two solutions I come up with are repeated solutions. I can plug in a value for n in the top equation as well as the bottom equation and get the same answer. All right? Question is, what values of n do I have to plug in there to make that happen? Well, again, look at your phase displacement here on your sinusoid. And again, we're not going all the way back to the beginning. We're going right to here where we kind of started a new problem. We said, all right, take the big problem and split it into these two. So the phase displacement here is 0. So that's our starting point. Right there's where we're crossing the sinusoidal axis and increasing. So with n equal to 0, since I'm setting this equal to a negative number there, I'm taking the sine inverse of a negative number. That solution that I get right there is going to be the sine inverse solution with n equals 0. So with n equals 0, my sine inverse solution right here. That's going to give me the one and only solution I want. But there is actually a second way to get that answer. Again, because we're setting this equal to the lowest point, there's two ways to get there. The other solution, we do this in another color, would be to consider what happens if we go back to the left. Maybe I should sketch a little bit more of this so I can see what's going to happen. So let's sketch right here, this part of it. All right, so if I go back one period, this would be where n is equal to a negative 1. And again, if you use the sine inverse solution from here, you're going to go back to the left even further. We don't want to do that. But from here, if I go to the right, the first solution I hit, which actually is that same one right there, that's the pi minus sine inverse solution. So, oops, except it's not pi, right? This is in degrees, so this is actually the 180 minus. 180 minus sine inverse solution. So this would be n equals a negative 1. So if you plug in n equals 0, sine inverse of a negative 1 is in fact a negative 90 degrees. That's the answer we're going to get. Or if I plug in negative 1, sine inverse of a negative 1, that's 90 degrees. So 180 minus 90 is going to be 90 degrees. And if I add on a negative 360 to that, we're going to end up with that negative 90 degrees. So there's our two solutions there. All right, let's take a look at example number 4. Example number 4 says to solve 0.2x plus sine of x is equal to 2. 0.2x plus sine of x is equal to 0.2, or is equal to 2. This should already make you a little bit curious, perhaps. Well, what exactly is going on here? When you have 0.2x plus sine of x equals to 2. Now, you just saw an equation that involved multiple thetas in it, so we saw how to deal with that. But here I've got a little bit more of a problem in the fact that I've got an x that's sitting here by itself versus this one is the sine of that quantity. I'm not going to have a technique that I'm going to be able to use to somehow, use a Pythagorean property or whatever to somehow convert this over so it's just all trig functions. There's no way to do that. So we're going to have to do this with another approach. And anytime you see a problem like this where you've got the sign of some variable and then that variable is also used somewhere else but it's not using a trig function, that all falls into this category of there's no algebraic solution. The solution for this is going to be a numeric solution. That's what we're going to have to do. And what we mean by that when we say a numerical solution means you're going to have to use your calculator in order to answer this one. But before we even sketch this and get onto our calculator, let's think about what's happening over here on the right. This is kind of an interesting equation that they've given us here on the right to deal with, or on the left side to deal with. If you think about the equation of your general sinusoid is c plus a times the sine, since that's what we're using in this problem, times b of x minus d. C plus a times the sine of b times the quantity x minus d. That's our general equation of a sinusoid there. And you can kind of match these things up here. If you look at this equation up here, you've got a sine, so that's obviously the same sine function that we're talking about. You're talking about this x value here. So this x that we've got here, that's all of this stuff. B would be 1, d would be 0. There's no phase display, or there's no amplitude for this, or the amplitude is 1, I guess is what we should say there. That is, there's nothing out in front of here. That would be the a value, that's 1. And I guess the interesting part for us then is this last piece here, the piece that's out front, this guy right here, that's our c value. Now c we know is the sinusoidal axis. And the sinusoidal axis is the line that goes right down the middle of your sinusoid. And so if you look at what they've got here, 0.2x, 0.2x is not a horizontal line. That's a linear function. It's got a slope of 0.2, a y-intercept of 0 there. It's got a slope to it, which means that if that's the line that goes right through the middle of our sinusoid, then our sinusoid must no longer be running horizontal, but it must be running at some sort of an angle. It must be headed up off our screen. Let's see if we can, in fact, sketch that and see what we end up with here. Grab your calculator and let's see what we have here. All right, so with our calculator here, let's punch in this equation in y1. And actually, we're going to do a little bit more than that with this. But we've got 0.2x plus the sine of x. And what I want to do is I actually want to sketch not only that equation here, but just so you can see the description that we were talking about, let's graph this c part that's out in front of this, the 0.2x. We'll come back and we'll get rid of that in just a second, but I want to show you exactly what's happening here. And let's just do this in the standard window. We're in radians here, so that'll be fine. And what you can see there is I've got the sketch of the sinusoid, like we said we should have here. I know it's sinusoidal in shape, but notice that that sinusoid is not oscillating back and forth around a horizontal line. It's oscillating back and forth around this linear function. That's 0.2x that we're oscillating back and forth around. And so you can see that your sinusoid is increasing as you go further and further to the right. It gets higher and higher and higher. All right, so we're trying to find all solutions there for where this sinusoid is equal to equal to a value of 2. So let's go back to our y equals menu. And now that we've kind of played around with this to see kind of what the sketch is going to look like and understand that equation, now let's actually solve the problem that they wanted us to solve, which was to set the sinusoid equal to a value of 2. So let's go ahead and graph that in the standard window here. And it looks like there's 2 solutions that show up there over to the right. It looks like there's probably going to be a few more solutions. So let's change our window here a little bit. Let's go from 0 to 20 instead of including that negative value, those negative values. They were not getting us any solutions anyways. There we go. It looks like we've got a total of 3 solutions here. That prior to that, it's not high enough to hit that value of y equals 2. And then after that last solution, it never drops down to a value of 2. It continues to increase higher and higher as you go further to the right. So the way that we're going to find these solutions is we've got to find the intersections. So let's do that. Go to your second calc, and I'm going to grab intersect. And you just have to pick your two curves there. I'll scroll back to the left of approximately where my first solution is that I'm looking for. But pick your two curves, y1 and y2. And then it asks you for a guess, approximately where's that first intersection. So I'll get your cursor there and press enter. And there's our first solution, 6.941. In fact, let me grab a picture of that. And we'll put those into our sketch here in just a minute. Let's do that again. Go to your calc menu and we'll do another intersection. And again, give it your two curves there and give it a guess. This time go over to the right a little further there. And 9.280 looks like our second solution. And again, I'll just grab a snapshot of that. And then finally, let's grab the last solution. Oops. Try that again. Give me your two curves and a guess of where it's at, and 12.126, it looks like it's about where the last solution is. So I'll just grab a picture of that as well. All right. So let me just copy and paste these into our sketch. All right, so here's our three solutions. Maybe I'll just line them up like this here since I can grab the answers off of them that way. All right, so for our work for this one, down below here, let's write down our equation that we are solving. I know we have it written up above there, but then we can immediately write our answers down from our calculator. So we had 0.2x plus the sine of x is equal to 2. That's your work, by the way. When you're solving this numerically, just show me the equation you're solving. And then let your calculator do the work here for you. It crunches the numbers and gets 6.941 is the first answer. Make sure you got 3 decimal places there. Second one's at 9.280. And the third one is at 12.127 if we round that. Or 126 if you just truncate it. So there we go. There are our 3 solutions. So if you can solve the problem algebraically, that's the technique we're going to use. On problems like this one that you see right here, where there is no algebraic solution, you're going to have to use your calculator to help you solve that. Just graph the two, find the intersection, and write down your solutions there. Make sure you're in the right mode, of course, when you go to graph that. Some of these will be in radians, some will be in degrees. And that right there is the end of the third part here of section 7.4.